Hello guys and welcome back to the channel, and today we are going to be talking about the subject pumping lemma, automata theory and its the computability of the topic pumping lemma and its applications. And my name is Paramitham, studying history at Venkateswara College of Engineering, pursuing fifth sem in the departments Computer Science, Engineering and Artificial Intelligence. Contents: Formal languages. What is pumping lemma? Key components of pumping lemma theorem, and pumping lemma theorem applications. Formal languages and their importance in computer science. Formal languages in computer science. Formal languages are essential in computer science for describing the syntax and structure of programming languages. Importance in programming. Formal languages play a crucial role in programming language design, compiler construction, and syntax analysis. Pumping lemma is a fundamental theorem within the realm of a formal language theory. The pumping lemma stands out as a fundamental theorem. Pumping lemma is a theorem in formal language theory that establishes a certain properties of regular languages. It provides a set of conditions that regular languages must follow. Key components of pumping lemma. Conditions. The pumping lemma consists of specific conditions that a language must meet to considered regular. These conditions involve the existence of a pumping length and the ability to split longer strings into smaller segments. Pumping length. The pumping length is a crucial parameter determined by the pumping lemma for a given language. It represents the length of strings beyond which properties guaranteed by the pumping lemma can be exploited. Now let's talk about proving non-regularity. Proof technique. The pumping lemma is often used in proofs by contradiction. The idea is to assume that a language is regular, apply the conditions of the pumping lemma, and then show that this leads to a contradiction. Non-regular languages. By demonstrating a contradiction, we can conclude that the assumed language is not regular. This helps establish the non-regularity of languages that do not meet the conditions of the pumping lemma. Now let's get into the core topics of the pumping lemma theorem. The pumping lemma theorem states that there exists a pumping length such that any string in the language of the length at least the pumping lemma can split into three parts x, y, z, satisfying the certain conditions, as you can see in the diagram, top right side. Pumping lemma theorem. For any regular language L, there exists a constant pumping length P such that any string is in S in L of length at least P can be written as S equals to XYZ, where the following conditions hold. For each I greater than or equal to 0, xy power I, Z belongs to L, modulus of y greater than 0, that is y is not non-empty, modulus of xy where less than or equal to p. Proof sketch. Assume L is a regular language and let P be the pumping length guaranteed by the pumping lemma. Consider any string S in L with the length at least P, that is modulus of S greater than or equal to P. Now let S equals to A1, A2 up to AK, where A of AI is the ith symbol of S. Since L is regular, there exists a DFA, deterministic finite automation, that recognizes L. Let Q0, Q1 up to Qm be the states of DFA. As S is processed by the DFA, it enters a loop of states due to the pigeonhole principle. More than P plus 1 symbols, but only P plus 1 states. During this loop, some state Q of Qi must be repeated. Let X be the substring of S before entering the loop, that is X equal to A1, A2 up to AJ. Y be the substring within the loop, that is y equals to aj plus 1 up to a1, and z be the remaining substring after the loop, that is z equals to a1 plus l plus 1 up to ak. Now consider the string s dash is equal to x y power 0 z, where y of 0 represents y repeated 0 times by construction. S dash is in L because it corresponds to the path x followed by the loop y repeated 0 times, and then z. Modulus of x y less than or equal to p. Since y is within the loop, modulus of y greater than 0. By definition, we know that y is within the loop. For any I greater than 0, consider S of I is equals to xy of I z. Each S of I is also in L because it corresponds to the path x followed by the loop repeated I times and then z. Now let's talk about the applications. First, the applications of pumping lemma theorem in language recognition, compiler design, lexical analysis, parsing and syntax analysis, network security, DNA sequence analysis, formal language research, and algorithm complexity. And if you guys have found anything information in this video, please leave a like and subscribe to my channel. Thank you.